Good evening, students. I'll start with the class. In the previous class, we had derived the formula for escape velocity. Escape velocity was nothing but the minimum velocity which you need, okay, to keep the means so that it escapes from the gravitational pull, so that it doesn't fall back on the earth. Any satellite or any body which has been sent out to rotate in the or revolve in the earth's orbit. So velocity which we had derived was escape velocity. V was This was one option. Then we saw in terms of G. Suppose we want in terms of G, then E was 2gr. In terms of density, we wanted to know, then it was 8 upon 3 pi. So these were the three ways we can express escape velocity. So for Earth, we know that suppose if we take this formula, V is equals to 2gr. We take G, you know that it is 9.8, and radius of the Earth we usually take as 6,400 kilometers for the Earth. So if we substitute these values here, then we usually get 11.2 into 10 raised to 3 meters per second, or in terms of kilometers, if you want to know, it's 11.2 kilometers per second. Because 10 raised to 3 meters means 1000 meters, nothing but 1 kilometer. Now there are some things which we should know about escape velocity. Escape velocity does not depend on, just a note, escape velocity does not depend on angle of projection. There is no theta involved in this formula. Okay, so it does not depend on which angle it is being projected. The second thing, escape velocity depends on mass and radius of the planet. That's why what happens is every planet will have different mass and different radius. So not necessary that all the planets of the universe will have the same escape velocity. Therefore, different planets will have different velocity. If you have sometimes a applicative question comes, does all the planets have same velocity? Give reason. So we know that different, we have to say that different planets will have different escape velocities. Why? The reason is escape velocity depends on mass and radius of the planet. So obviously different planets will have different mass and radius. Not all the planets have same mass. Different escape velocity. If you just want to know for information, Moon's is 2.3 kilometers per second. Mercury is 4.28. Earth is, we know already, 11.2 kilometers per second. Jupiter is 60 kilometers per second. And Sun is, it's just basically calculated based on the formula, based on the mass and the radius. Even though it must have not been tried practically, just assumption sometimes using the formula. So the same formula which we apply for Earth, the same formula must have been applied for this and then calculated. We had seen something called as that critical velocity. The critical velocity is also called as orbital velocity. So we'll derive one formula for that also. Or also called as critical velocity, VC. You know that horizontal velocity of the rocket. First, what happens? The rocket is launched vertical at this first stage, then it goes in the second stage, and then the moment it leaves, it has a vertical speed, horizontal, sorry, horizontal velocity. So that velocity always has to be equal to some critical velocity, which I told you, which is same as your orbital velocity, so that it remains inside the orbit of the Earth. That otherwise, what will happen if it is more? I told you it goes outside, and if it is less, then it will fall back to the Earth. So this velocity is very important for any object or any satellite to remain within the force of the gravitation without falling on the ground back or without going out of the line. Okay. So it is nothing but the horizontal velocity of projection, means of that rocket, whichever is being projected, required to put the satellite in the circular orbit around the Earth. Is called orbital velocity or critical velocity. So this is the definition. The horizontal velocity of the rocket or the projection required to put the satellite in the circular orbit around the Earth. So we'll derive this. Now this is the Earth, suppose, of mass m, capital M. Now this is the planet, this is the satellite which goes, okay, which has been launched from the Earth. Suppose this height is h and radius of the Earth will take as r. This is your Earth orbit. Now this is that horizontal velocity view. At every point it is like this, like it's just taken like the tangential type. Now although the arrow has been marked like this, doesn't mean it is going out of the orbit at that particular point. Then the moment it goes there, again its horizontal component has been shown. Just a horizontal component, not that this is going out of the orbit. Just the word horizontal velocity means the horizontal component. Consider Earth as a spherical body of mass capital M and radius r. Now let m small m, this is capital and this m the mass of the satellite projected from Earth's surface at height h. From here to here it is been projected. Let v naught be orbital velocity of the satellite. Now this is the normal data. Now these are like the two bodies. One Earth is one body and the satellite is the second body. So whenever there are two bodies in the universe, we know that there is always a force of attraction between them. And this is told by Newton's law of gravitation. So by Newton's law or Newton's law of gravitation. What is the formula? G m1 m2 upon r square. This formula we know. Starting of the chapter we have seen. Now only thing you have to change accordingly this side I'll write m1 g m1 m2 upon r square is the formula. Now these different letters they are used for the derivation. So accordingly we have to write. G is anyways the gravitational constant. M, if you are taking mass of the earth, one will be capital and the other one will be of the satellite. One mass is of the earth, the other one is of the satellite. And now r is nothing but the distance between the two bodies, always measured from the center. So if you measure total from the center to here, it is nothing but r plus h, total distance from here to here. That will be equation 1. Now, whenever any object, now the satellite is moving in a circular path. Whenever circular path is involved, you know that the velocity which is involved is the force which is involved is the centripetal force for circular path. The centripetal force will come into picture. So what is the centripetal force? Given by just mentioning C because therefore centripetal force. Fc will be equals to, what is this? mv square upon r. This is the formula for centripetal force. Now here it will be m. Who is pulling it? The earth. So this mass will be here. What is the velocity here now? Inward. That is the orbital velocity. The velocity of the satellite is v naught square upon distance. Distance will be from here to here. The same thing. R plus h. This formula we already know. We have to just modify this formula according to what status we have taken for the derivation. Now when will this be attained? Whenever this force between them and this centripetal force is equal. Otherwise what will happen? If this center of force of attraction is more, then the satellite will fall. Okay, if the earth's gravitation, whatever attraction between the two bodies is so high compared to this centripetal force which is trying to keep it on track, if there is a disbalance between them, then this fellow will never lie in the orbit. Either it will move out or it will fall down. Only at equilibrium, means when this force is equals to this, then only it will remain in the path. If one of them increases or decreases, then the balance will be lost and the satellite will fall out of the orbit. Okay, so at equilibrium, that is when you have to maintain the orbital path, your centripetal force should be equal to your gravitational force. You can mark this as equation 2. So this should be equal to this. So substitute here, substitute this one here. Both other way also you can write, gravitational force equals to centripetal force. Whichever way you write doesn't matter. So mv square, this will be, now our aim is to find the orbital velocity, basically this. So only this which I want to find, I'll keep it on one side, rest of the terms I'll take it on the other side. So we not where I'm keeping here, take this on the other side. G m upon r plus h already there. Now this will go up and m will be down. This will go down, this will go up. Now what all is getting cancelled? M and m will cancel. So one of this will cancel with square. It's basically, this is x square and this is x. So what remains is v naught square is one more m was there, no? Here, 1 second, where is it? Will be a small one. Centripetal force, no? In the equation, you have to use small m. Because mass of the satellite and orbital, well, just correct this, Fc will be equals to G, this won't be there. 1 second. Gm. Small m you use, huh? Because this is mass of satellite. And this is velocity of satellite. So instead of capital M, just make the small m. So this will be small m. This will be, then is correct. Only thing this will be small m. Small m will get cancelled. Because the formula, it has to have capital M. Final one. If you cancel this, we'll get small m here otherwise. So G m upon R plus H will remain. In equation number 2, just make the small m. And here also. So m and m will cancel. So V naught will be nothing but R plus H. If you know the final formula, know what you need to get. Sometimes any mistake in the in between, you can always track it. Because you should know what answer you should be getting. So if you have done some mistake somewhere in the middle, you can always find out. You are not getting the correct letter. But if you simply by heart and go and you don't know what you are supposed to get the final answer, then you will be lost. Now this is your orbital velocity. Now this is for some same how we had this derived 3 ways how we could do no for escape in terms of, suppose if I want in terms of gravity. This is one case in terms of gravity if I want. So we know this formula G is always Gm upon R square. So what will be Gm? Gr square. So instead of Gm, we can put this value of Gm in equation 3. So instead of Gm, put Gr square here. So what I'm putting here, Gr square. Then one more way to express another case. In terms of acceleration due to gravity at height. So we know that Gh is nothing but Gm upon R plus H the whole square. So what is the value of gm here now? Gh into r plus h the whole square is gm. Just take this up. So now you can put value of gm in equation 1 or equation 3 it will be, no? We had marked equation 3. What was equation 3? V naught was gm upon r plus a. This was the formula which we had got. So put this value now over here. This is a subscript, small letter for gravity due to height. Now this whole thing will cancel with one of them. So answer will be gh into r plus h. Do another way. In the third case, when the satellite is very close, whenever the satellite is very close to the Earth's surface, we have to assume h to be very small compared to r, the radius of the Earth. So what we can do, we have to ignore that h. Suppose this Earth is quite big and comparatively the height is very small compared to this big radius, then we have to take almost equal to 0. Okay. So we have to take height as almost 0 compared to the radius of the Earth. So equation 3, same, everything, whatever is the case, you have to put it in equation 3 because equation 3 is the main formula. This was the answer which we had got for velocity. Now here we have to put as 0. Answer will be gm upon r. And this is when satellite is very close to the Earth. Next is the geostationary satellite. So these were the derivations for this orbital velocity. Now one last small topic, geostationary satellite. What is a geostationary satellite? It is also called as geosynchronous or communication satellite. You must have heard of this term, geosatellite. See, whenever you send any, this is Earth. Now there will be so many satellites which will be sent in the orbit. Okay, not necessary it's only this one particular line. It's like basically almost a range of like a strip. There will be various satellites here and there around the Earth. Now they will be having their own speed of revolving around the Earth, okay, based on how they are programmed. Now, if a satellite is programmed like to behave just like a Earth, like the same time how much Earth is taking, okay, this now the satellite will be revolving as well as rotating about its axis. Now you know that Earth will be rotating also at the same time and revolving also. So if this satellite is behaving just like Earth, okay, same moments like Earth, time period of that rotation as well as revolution is same as that of Earth, and it is called as a geostationary satellite. Not necessarily all the satellites behave like Earth. So only those satellites who behave like Earth are called as geostationary. Otherwise, they are called normal satellites. So this is a word given only specific to those satellites who behave like Earth. So geostationary satellite, it is a satellite whose direction of motion is same as that of the rotational motion of the Earth around its axis, and also time, how much period, 365 days and 365 that period of revolution around the Earth is exactly same like Earth rotation, exactly 24 hours. So what happens, although the Earth is also moving but with the same speed, what is happening, the satellite is also moving. But if a person is standing on Earth and trying to look at that satellite, no, he will think that the satellite is at rest only, because when the Earth is reaching here, means suppose you are standing, after some point the Earth is moving but we don't realize it. At the same time, if this satellite was here, it will reach here because it is following the Earth's motion. So for you, it will look there as if it is there only. So that's why the word stationary is there, because it looks like it is at stationary, means it is at rest compared to your side. But suppose if there was a satellite which remains here only in the orbit, that is not following, but Earth was moving and you reach here, according to you, now this satellite will look far away. But geostationary, it is moving with the same speed as of the Earth. So for you, it will look like as if it is there only at rest. So the satellite always appears as stationary. Stationary means at rest. Above the certain place on Earth. Usually the height is, it revolves at a height 398 0.35890 kilometer, which is approximately 3,600 kilometers from the Earth's surface. And its orbital velocity is 3 kilometers per second. So this is all what we need to know about a geostationary satellite. So its rotational motion is same as that of the Earth in exactly 24 hours. Satellite always looks stationary from the one place of the Earth if you are watching. So from the next topic is actually the Kepler's law, but Kepler's law has been deleted from the portion as per the NCERT portion, so that I will not be doing. Only if it is done in your college, then let me know. At least the ones which I have asked, their colleges, they have not done Kepler's law. Some of them have not completed the chapter, so that's why I have not asked. Okay, if it's done in a college, once the chapter is completed, if Kepler's, this is something called as Kepler's law has been done, then just let me know. Otherwise, it's not necessary to, because it's clearly mentioned that in the deleted portion, Kepler's law is not there. So if this is not there, the normal theory part and the derivations, all the derivations which are there under the chapter I have done. And a few problems I will solve. Question 1, they are all mixed problems. So calculate force of attraction between two balls, each of mass 1 kg each, when their centers are 10 centimeter apart. Given G is 6.67 into 10 raised to minus 11 Newton meter square per kg square. So what all data has been given? There are two bodies, two balls which are of mass 1 kg. So the mass is both m1 m2 is 1 kg. Distance is 10 centimeter, which always has to be in meters. Centimeter means you have to always either multiply or you have to divide by 100. So it's 0.1 meter. G has been given, so force of attraction has been also. So it is G m1 m2 upon r square. Both are 1 kg, 0.1 square. 0.1 means 10 raised to minus 1. Same as 10 raised to minus 1. So this will give me 10 raised to minus 2. If you take it on top, it will become plus. So 6.67 into 10 raised to 9. Forces in terms of Newton. Next question. If the earth was made of lead, which had a relative density 11.3, then what would be the value of acceleration due to gravity on the surface of the earth? Radius given as 6.4 into 10 raised to 6 meters. G is given as 6.67 10 raised to minus 11 into 11. Correct. Minus 11. Now there is something called as relative density is been given. Something like this is given. The relative actually density formula is when we are comparing the mass of the surface, density of the surface with compared to the water. Relative density is always equal to density normal density, okay, of whatever surface you are comparing, the density of water. This is the normal ratio. So this is the density which we have to calculate for the earth. So this will have to take up. Will be an actual rho, what we are calculating. Now relative density has been given to me as 11.3. This, even though now this density of water has not been given, no. So remember that density of water to be taken as Sometimes they mention, sometimes they don't give. Into 10 raised to 3. Okay, so this is given as 11.3 and this will be 10 raised to 3. That will be our rho. Now acceleration due to gravity on the Earth's surface has been asked. So we already know this formula. So many times we have used under derivation. What is in terms of g? Suppose you want to know, then it is r square. Now only some time back only in the derivation also we used this formula. Acceleration due to gravity. Suppose you want to know on the Earth's surface. Now mass has not been given. We know that density is mass upon volume. So what will be mass? Density into volume. You know the density we already know how much it is. 11.3 into 10 raised to 3. And volume is nothing but volume of the earth. So we are assume it to be sphere. So 4 by 3 pi r cube will be our mass. So put the value here while calculating the problem. So g we have to calculate. This already has been given. Now this mass will be this value 11.3. R is the radius of the earth which is already been given. So substitute them. Okay, everything has been written. Upon there is r square. Now what you can do? This and this you can cancel. Okay, one r only will remain. This is r cube and this is r square. So I have cancelled this. So 1 r remains. And r already given to me 6.4. So you can substitute. First also you can substitute and then cancel r, no problem. So 22 by 7 we can take pi value. And r is given as 6.4 into 10 raised to 6. All the powers you can add. So minus 11 plus 3. So this will be a basic one. So if we had assumed almost 6 point to this, 6, 6, then you can directly cancel also. Otherwise you can take this as 21. So it will be 6.67. All the numbers I'm writing together. 7 3 are 21 into 10 raised to minus 11 plus 3 plus 6. So you can divide this 22 by 21. So around 1.4. One 1.04 it will be, no? 10 is
Yes,
not
you
good.
haven't multiplied 6.4.
There it is there. This 6.4 is also there. I'll write here in front. 6.4. Approximately 1.0. And then this will be 9 minus 2. So all the numbers then to be multiplied. We'll get approximately 22.21 meters per second. Gravity, so meter per second square. Next question. Acceleration due to gravity. At moon's surface, 1.67 meter per second square. If the radius of the moon is 1.74 into 10 raised to 6 meter, calculate the mass of the moon. Sometimes they'll say the word, use the known mass value of G. Use known value of G. So that we know that it is 6.67. Acceleration due to gravity, the only formula which you can think is given as 1.67. It will not be 9.8 now, or different values it will. 1.67 G is 6.67 into 10 raised to minus 11. M we have to calculate. R is 1.74 into 2 square it is. So this whole thing will go up. Now while squaring, both will get squared. So basically I'll write it separately. This multiplied will give me 12. This whole thing will come down. This minus will go up and become plus. And if we are removing the decimal point, 2 decimal this side, 2 decimal this side. So I can write this as straight away 167 into 1.74 the whole square into 10 raised to 12. This will go up, become 11. And this will become 667. So answer what we will get is 0.758 into 10 raised to 23 kg. Next question. Find escape velocity of at the earth given its radius and g equals to 9.8. So now the formula to be used. Now many formulas are there for escape velocity. Now value of g is been given. So the formula to be used is in terms of gravity of acceleration has been given. The escape velocity will have to use this formula in terms of gravity. In terms of density was given, then the third formula would have been. And suppose mass was given, then the first formula. So basically what has been given, accordingly you have to use. So mass then first, gravity then second, density then the third formula. Now this is simple enough. 2 into 9.8. This we have already done. Before also I had explained. It ends up to be around 11.2 escape velocity of Earth. So we'll get like this. Square root of this would have been 10 raised to 3. Which you can write it as 11.2 kilometers per second. 10 raised to 3 is nothing but 1 kilometer. Next question. Determine escape velocity of a body from the moon. Consider moon to be a uniform sphere of radius 1.76 into 10 raised to 6 meters and mass 7.36 into 10 raised to 22 kg. Now again here escape velocity only has been asked. But now check what data has been given. In the previous problem, g was given, acceleration due to gravity. So that's why we had used the second formula. Now here mass and radius has been given. So we'll have to use the first formula, main one which we had derived. This one we had derived. So Why we are using this? Because mass has been given and radius has been given. G we anyways know, 36.67. So G is anyways 6.67 into 10 raised to minus 11. M is been given. This is radius and M is 7.36 into 10 raised to 22. So just have to substitute. So you can basically transfer these values. So this will be 2 into 667 into 176 into 7.36. So if you are removing any 2 points, no, we have to add. You can do like this also. You are making the 736. These are balanced. 2 you shifted here, 2 you shifted here. If this you are shifting this side, you can just multiply on top by 100. If you don't want to deal with decimal point, and write all this together. So this is into 10 raised to minus 11. On top, if I'm bringing, this will become minus. It will become minus 6. M is there on top, no? No one noticed. I substituted it down by mistake. So I'm thinking how I'll get much less. Or M will be here on top. Because so much of negative number was coming. It can't be so less also. Minus 22 was turning out to be. G is this, M is this, R is this. Normal. Now you can shift. Now it's correct. 176 this will become. And this will be total 10 raised to minus 11. This will go up, become minus 6. This will become plus, anyways, plus 22. The last one is 7 point. Answer will be 2375 meters per second. Basically, it will be what? You'll get this way approximately. And then after multiplying, you may get like Next question. An artificial satellite revolves around the Earth at a height of 1000 kilometers. The radius of Earth is 10 raised to 3 kilometers. Mass of Earth and G is 6.67 into 10 raised to minus 11. Find orbital velocity. What all data has been given? You write height is kilometers. If you want in terms of meters, you can convert. Right? R is 6.38 into 10 raised to 3. Now, there's a height involved. So we have seen the orbital velocity formula in terms of height. Whenever height has been given, so the orbital velocity formula is Gm. This is normal. Suppose if it was asked acceleration due to gravity, suppose small g was given, then you have to use the second formula. But now nowhere there is small g given. So you have to use the normal first formula. So g is 6.67 into 10 raised to minus 11. M is 6 into 10 raised to 24. Both are in terms of kilometers, no? So that will be 7 point. How much has been R given? Total 6.38 into 10 raised to 3 plus 1000. Means basically you have to multiply it by 1000. If you are taking it by in terms of meters, then it will be like the 6.68 into 10 raised to 3. Velocity, mostly it will be meters per second. So if you are multiplying it by 10 raised to 3, then it will be total 10 raised to 6 meters. This will be same way 1000 into 10 raised to 3, which will be total 10 raised to 6. We take it as 10 raised to 6 only. Because velocity we'll have to write in terms of meters per second, no? So this is given in terms of kilometers. So better we write. Otherwise we'll have to write in kilometers per second, which we may forget to do the conversion after the problem. So before that only if we do, it's better. So directly we'll convert it into meters so that there is no confusion. Now this you can easily solve now. Why? Because this is 10 raised to 6 you can take out common. So 6.67 into 6, and this will get added. Now 6.38, what will be left is 1. 10 raised to 6 will be common. And then you will get this as 7.38, and this will go up. Two decimals you can shift both the places. So 67 upon 738 into 6 into 10 raised to, this will be 13, 17, that will be 7. So answer will be if we had not used this 10 raised to 6 conversion, then it would have been kilometers per second. The answer would have been 7.36 kilometers per second. But in order to avoid that confusion of writing kilometers, best option is to convert it in meters and then calculate an answer. Suppose in the same question, I am not given in the theory part now. There is a formula for time period. That is actually just write on the theory part also and keep on. Suppose if you asked, also calculate time period of revolution or revolution. The formula is, suppose you want to calculate the time, 2 pi upon orbital velocity. So if time period was asked, we have to just substitute a value. Whatever orbital velocity you got now, you'll have to substitute it here. So 2 pi, anyways r plus h we had seen. How much we had got? 6.38 plus 1 into 10 raised to 6 we had got. And orbital velocity is 7.36 into 10 raised to 3. And then you have to calculate. This you can take as 22 by 7. So approximately we'll get 6297 seconds. One more question. An artificial satellite is going around the Earth close to its surface. What is the time taken by it to complete one round? Given radius of Earth is 6,400 kilometers. Now, what is the time taken by it to complete one round? So basically, time period has been asked. But in order to calculate the time period, we have seen that the formula is upon V naught. For that, we need to know what is escape velocity. That is, orbital velocity we have to know. So first we'll have to calculate how much is the orbital velocity. Now what has been given? Close to its surface. So this is a special case we have seen under the problems. Whenever close to the surface has been given, you have to take h as 0. Now we have seen two formulae for velocity, orbital velocity. These are all the possible formulae we have seen. In terms of gravity, this one is there, or in terms of gravity due to height, this one was there. And then when h was 0, the special case, we had seen that gm upon r. Now out of this, everywhere, now h will be 0, whichever formula we take. The problem is which formula to take to calculate your orbital velocity. What has been given? Only radius of the Earth has been given. Now we cannot use this because this is involving mass. We don't know what has been mass of the Earth been given to us, not given. This also we cannot use because gravity at a height has not been given. Now this also we cannot use. Again, we don't know what is the mass of the Earth. Now the only formula which we can use is this, because g is 9.8. We know that because it is Earth. Where the surface of the gravity it is fixed 9.8. We can use this. Radius has been given. So either this we could use or this based on now what data has been given. Since mass is not given, we have to use this. So we can use V naught is g r square upon r plus h. But h we have to take 0 because it is close to the Earth's surface. So this will be g r square upon r. One of the R will cancel. So gravity will be 9.8 and radius will be 6400 into 10 raised to 3 kilometers to meters. So this will be 7290. After calculating your orbital velocity, now you can calculate your time period. Again, for time period also, you can take h as 0. Now substitute. R is 6,400 into 10 raised to 3 upon this value 7290. And then calculate your answer. So you'll get around 5079 seconds. Unit will be second. So I'll stop here.